workbook, physics, mechanics, and now we are on to not too much left in mechanics. We're coming to the end of mechanics. We did conservation of momentum last time, so now we're on to circular motion. Right? Yeah. No. Okay, let's start. You can write this down. It's a big lesson today. It's a big topic. What did you do in maths at 10 o'clock?
Did one example that was new and the rest was all revision.
It was a tutorial?
Not really a tutorial, she gave us a sheet that was practice for her.
Right. Okay, circular motion, you got that? Yep. Right, so, what are we looking at? A couple of things to look at. Right, so first things first, we need our words. The words for these parts of the circle. So, I hope you all know what this one is called. What's this part called? Theta, yeah, and what does it measure? Angle. Okay. The or? Radius. Good. And the S?
Surface.
No. The length of the angle.
And there's a word for that. So, a circle. Theta is the angle. R is the radius. Does anyone want to tell me the S? Kim, any ideas?
Arch.
Go on.
Arch.
How do you spell that?
A-R-C-H.
Oh, A-O-C.
There you go, right. Arc length. Arc length, yeah. Yeah, that's it, very good.
It's too hot today.
It's nice, isn't it?
Yeah, but the temperature only 3 or 5.
Yeah, but you cycled.
No, sir.
No cycle today. Okay. Okay, did you write those words down? Yeah, good. I think it's also good if you draw the picture too, please, because it'll help. Yeah, did you draw this? Yeah. Okay, continue. Yeah. So, in physics, when we talk about motion in a circle, we don't use degrees. So you know in maths, when you're measuring an angle, something like this we say is 90 degrees. You know this in maths, right? But we don't actually use degrees in physics. We use a different unit called the radian. Now, what exactly is the radian or the rad? So does anyone know how we define this angle, this unit for angles? Like, how big is 1 radian? Anyone know? Roughly. Anyone know? Not 90. It's roughly 57 degrees. That's how big a radian is. So it's actually a big unit, 1 radian is a big angle. Why 57.3? You'll find out in maths class. But we say 1 radian is 57.3. In fact, if you're wondering, it's not exactly 57.3. If you want the exact number, it's 180 over pi. Yes, yeah. For physics, it's important because the formulas we use on the next slide, those formulas only work if we measure the angles in radians. Okay, so in physics we only use radians when we're moving in a circle. So I think this is enough for you to write down. You don't need to write down the reason it's important as explained in math class. But I think you should write this part down here. Got this? What's funny? No, share with me. What's so funny? No? You don't want to share?
No, I thought so a long time ago and they were still writing.
Ah.
So I thought I missed something or not.
Maybe you write very fast. Possible. Okay. Well, it's also Chow likes to write a lot. Chow makes good notes. You write down a lot. Okay. Continue. Right. Okay. So here are two small questions I want you to do on your calculator. I want you to change a quarter of a radian into degrees, and I want you to change 30 degrees into radians. Let me open up my calculator too. No? What's going wrong for you, Matt?
I got 0.0003.
Oh, yeah, it sounds a bit small, isn't it? Okay, who has an answer for the first part? Chow, you got the first part?
I don't know how to calculate this one.
Ah. What about the second part?
Same.
Same? Andex, you got the first part?
Yeah, 14.33.
What is it?
Yeah. 14.33.
14.
Yeah.
Yeah, sounds about right. So 0.25 radians. But how big is a radian? It's like 57.3. So multiply 57.3. So that's about 14.3 degrees. That's what you said.
Yeah.
That was correct.
I see, you do know how to do it. Believe in yourself. Right, the second one then, 30 degrees into radians.
0.524. Maybe. Yeah.
0.5
24.
sounds about right. So look for the other one. 30 degrees. Okay. Now we know that 1 radian equals 57.3 degrees. So you can say 30 degrees equals 30. I'll just write degrees like this, DEG, 30 degrees. Okay. That's equal to 30 over 57.3 times 57.3 degrees. Because I just multiply the top and the bottom by 57.3. Now, why did I do that? Well, what is this? What is this? It's a radian. So this is 30 over 57.3 rads. Which you have that there, George, what is it? 0.524 rad. Is this one okay? Kim, is this okay? Yeah, Andek?
Yeah.
I remember back in my high school, the teachers like times pi divided by 180.
Yeah, same thing. Like 57.3 is the pi of the 180, you know. You can do that, math. You can use that if you like. It's fine. Okay. Continue. Ciao.
Yeah.
Yeah? Are you sure?
Yep.
Okay. Right. Now, we've seen two types of motion so far in physics. We have SUVAT in one dimension, and we've also, like a car, you know, easy. And we also seen SUVAT in 2 dimensions. What motion is that we did in 2 dimensions? What's that called? What was the motion in 2 dimensions? Projectiles, yeah. Don't be confident. Projectiles, yeah. Projectiles. Okay. So we're now looking at a new motion today in 2 dimensions called motion in a circle. So firstly, what makes motion in a circle? Like, why would something move in a circle? So if an object is moving in a circle, does anybody know why or what makes it move in a circle? So, for example, when you fire something, it goes like this. Why? Simple. Because there's one acceleration acting down. And that's it. No other acceleration. And this is G. Okay. Does anybody know what it is that makes something move in a circle? Why would something move in a circle? Any ideas? Yeah, but something special about it. Like, obviously the force can't just point any direction. There must be something special about it to make it move in a circle. Not so specific, just in general. No? So, you sure nobody knows this? I think someone knows it deep down, but is too shy to say. Andek? No? Kim? Are you sure? Okay. So, if something is moving in a circle, then it's because the force that acts on it is perpendicular to the velocity and towards the center. So in other words, as a picture, if this is moving in a circle, it's because there's a force acting on it that points to the center of the circle, and it doesn't matter where it is. So if it's here, the force points to the center. Okay? And also, it's perpendicular to the velocity. So this guy is heading north here, to the north, and the force here is perpendicular to it. So this one here, heading this way, and the force is perpendicular. So if you picture here, can you imagine the force is this way? And its velocity, perpendicular, so it's this way. Now, in your maths class, does anybody remember the name of something like this line on the circle, which is perpendicular? Yeah, good, okay. So, V is a tangent. Okay, and F is towards the center. That's what makes something move in a circle. Okay, so you can picture when you have something on a string, you know, because the string is to the center, but you turn it around. So the force is to the center. Yeah. So this is the definition, and they have asked it in the exam a couple of times now, maybe three, 4 times. You don't need the words exactly the same as this. In the exam, the key words they want to see is acting, that the velocity is perpendicular, they must see that, and they must see you say that the force is towards the center. Okay? You absolutely must have those two things. Now, you don't have to use my words, but you know, here it is here, if you can write that down. What's that, milk, is it?
Soy milk.
Soy milk.
Yeah.
Okay, continue. Yeah? Good. So I already drew the picture for you. Okay. Now, this force has a special name that makes something move in a circle. We call it the centripetal force, and it's the force that makes something revolve to move in a circle. This force is what keeps it in a circle. So you don't need to write all of this down. Okay, don't write all of this down, but at least write down that centripetal force is the name of the force that makes it move in a circle. We call it a centripetal force. You can pronounce it centripetal or centripetal, whichever you like. Before I said it, how would you pronounce it? Central. Ah, yes, very good. That's actually how they pronounce it in India. That's how my Indian students say it. Centripetal, yes. Okie dokie. Yeah. Yeah. And of course, obviously, it's directed towards the centre. So, F equals ma. Imagine that m was 1 kilogram. So then we can have F equals a. Basically, the point I'm trying to make is that if there's a force directed towards the centre, then there's also an acceleration directed towards the centre. And in the case when there's 1 kilogram, it's actually the same, because F then would equal a. So, no shock to discover that centripetal acceleration is the acceleration towards the centre. Same thing as centripetal force. Okay. So, just write down centripetal acceleration comes from centripetal force. That would do. Centripetal acceleration comes from centripetal force. Chow likes to write down everything. Everything is good. Ah, you all going to the Halloween party tomorrow?
Yeah.
Have you got costumes?
No.
Ah, you should get something. Anybody?
I'll just wear a shirt and that's it.
Ah. I'll be dressed up. You get to see my costume tomorrow.
Can we know it now, or is it going to be a surprise?
I'll leave it as a surprise.
Okay.
Well, have a guess. What do you think I might dress up as? Last year I was Stephen Hawking. It's true. I printed out a face mask and I got the voice synthesizer on my tablet, you know. And I used an office chair as a wheelchair. So I'm allowed to do this because I'm a physics teacher, so it's okay. Any costumes for you guys? Okay, you're not? Are you going? Got a costume? No costume? Okay. I think sometimes you give a prize to the student who has the best costume.
It's going to be a best.
I'll give you a little tip if you want to win it, okay? It usually goes to somebody who makes the costume themselves instead of buying it from a shop. You know what I mean? So if you can make something yourself instead of buying it, it gives you a good chance of winning. It's my little tip for you if you decide to dress up, okay? Right. Now, some more definitions. There's a lot to do in this lesson. Angular velocity. Has anybody heard of this term before? Could you? No? You think you have?
I have, but I don't know.
You couldn't explain it?
Yeah, all of these terms are just familiar.
Okay. Well, we all know what velocity means. So what do you think the word angular means? It's an adjective. It's an adjective of what? Angular is the adjective. What's the noun?
Direction.
No, look at the word angular. What's the noun? If angular is the adjective, angle is the noun. So what do you think an angle velocity could be?
The speed is rotating.
Yeah, it's kind of like how quickly the angle must be changing. So the angular velocity is the rate of change of the angle. Now, what units would that be? Now think, velocity is meters per second. So what might angular velocity be? What might we think?
Degrees per second.
No.
Radians.
Yes. The units are radians per second. I hope that makes sense, because it's how many radians you can change in a second. So have a look at my hands. What angle would you say that is? Roughly what angle? Yeah. So, but we're using radians. So, I don't know, roughly, don't calculate it. How much is 1 radian?
Oh, 57.8.
Yeah, so what would you say that is then?
57.8.
Yeah, so a radian.
Yeah.
Radian, okay. So 1 radian a second would be if the angle moved this quickly. 1. You know, so that speed there, that rotating speed, that would be 1 radian per second, okay? Now, it measures how quickly the angle is changing. For example, well, I've already done my example of 1 radian per second. Okay. Now, here's another one. Periodic time. What could that be for the circle? Periodic time. Now, the word periodic you should know from your math class with Joan. You did your sequences. Remember the word periodic? What does it mean?
The number
Bit too weird for me. What was a periodic sequence? Like, what does the word periodic mean? It repeats, okay? So what would be the periodic time? What do you think?
the time for
Yeah. Periodic time is the time for 1 rotation, 1 revolution. This time. So, for example, you know, if you look at this hand here, this one moving, what's the periodic time of this guy? How long does it take it to go around once? 60 seconds. Okay, so a big periodic time means it's moving slowly. Okay, sorry. So the periodic time is the time taken for 1 orbit to be completed, and of course the units are seconds. So what did you say you did with John? What's the last lesson you covered? Did you do limits? Limits. Okay, you got that? Yeah. So if t is 2 seconds, then it takes 2 seconds for 1 orbit to be complete. All pretty obvious, I hope. Okay, now the units per second, or s minus 1. This is actually a special unit in physics. It's actually given I mean, you can call it this, but it's actually given a special name. Does anyone know what s minus 1 is also called in physics? The special unit. Have you ever seen it before? Yeah. The unit s minus 1 is often called a hertz. 1 hertz is called 1 per second. So whenever you have, you know, if you had something like x equals 5 per second, you can call that 5 hertz. So the per second is also called for hertz. Now, why do we have this unit? And the reason is because of this thing we call frequency. Now, what does frequency mean? You should know this word from English. What do we mean when we say frequency? Let me think. Kim, any ideas? What do you think? Come on, yeah, good, yeah. How many times? Yeah?
Per 1 second.
Good, very good. So the frequency here is how many times it can complete an orbit in 1 second. So the frequency f is the number of orbits in 1 second, and the unit is the hertz. Got that? Yeah? Yeah. Okay. So, if the frequency equals 2, what does that mean? So, if f is 2, what is happening? So, and maybe you can describe. If f is 2, what's happening?
2 orbits in 1 second.
2 orbits in 1 second, yeah. So, if f is 2, then there's 2 orbits in 1 second. Okay? Chow, I'll ask you this. If f is 0.5, what does that mean?
It's the
It's a hard one.
for half minute. No, it's well.
Yeah, 0.5 hertz. What do you think that means? So Andex said 2 hertz means in 1 second it goes around once, twice. So what do you think this means? I believe in you. I think you might know. Tell me what you think.
It's getting slow.
It's slower for sure, yeah.
Uh,
What do you think? In 1 second, what does it do?
a half.
Half a turn, yeah. Half a turn in a second, yeah. So, if it's 0.5 hertz, then only half an orbit is done in 1 second. Okay? Are we happy with this idea of frequency? Yeah. So, just like with UVATS, we now have some formulas. And you don't need to prove these formulas, they're too advanced, the proof. So I'll just give you the formulas. So the first formula is T is equal to 1 over F. Are you okay there, Kim? What happened? No. You like to use bad words in my class? That's okay. I'm old enough to take it. We don't have any minors in here that shouldn't be hearing bad words, do we? Is Andek a minor?
Yes.
Oh, maybe Kim will be a bad influence then.
I'm old enough to get it.
That's okay then. Alright, so that's the first formula. The second one, the omega is equal to 2 pi over t. So if you know the omega, you can know the t, and if you know the t, you can know the omega. And likewise, if you know the t, you can know the f, and if you know the f, you can know the t.
Omega is the
Angular velocity, yeah.
It's a W.
It's a Greek W, so it's not really a W. It's the last Greek letter in the alphabet. You know, the first one is alpha, and the last one is omega. Okay, continue. Yeah. V equals omega or. Now, just so you're clear what I mean by V. So, if you imagine a car moving in a circle, okay, it has 2 velocities. The first velocity is the omega. Now quickly the angle changes. The second velocity here is the meters per second, how fast the car is moving on the ground. And actually you can link the omega with the V. You can convert between the two by using this formula, V equals omega or. Okay, so you got that one? Yeah. Right, next formula. The acceleration equals V squared over R. That's number 4. And the good news is it's just the 4. So we'll have a look now, I think, at some examples. Okay, you got those 4? Okay, the first one is a kind of silly example, yeah?
So V equals to omega r, that the r is the radius, right?
Yeah, the ortho radius, yeah. Okay, Now this is kind of a silly example. CD, if you know what that is, spins at 500 RPM. What's an RPM?
Rounds per minute.
What per minute?
Rounds.
Rotation. Revolutions actually, but I understand your meaning. So in 1 minute it goes around 500 times. Okay? And I want to know what's the omega. First let me write down the F. So the F is, well no, first let me write down 500 turns per minute. Now that's not really useful because what units do we use? We don't use minutes. What do we use? Seconds. So what should I do first? I should what?
Times by 60.
Times by 60 or maybe divide by 60? Divide by 60, yeah. Okay. So I can change that into seconds now. So what is that now? 8.333 turns per second. But what letter is that? A, omega, V, T, F. What letter is this? 8 turns per second. F. Yeah, because you're saying in 1 second it turns 8 times in 1 second. Okay? So, what was I looking for? I was looking for the omega. Which formula can I use to get the omega? Which one should I use?
Omega equals 2 pi over t.
Yeah, now look here. Omega equals 2 pi over t. But do I know what the t is? No. But do I have a formula for t? I do. What does t equal? 1 over f. Yeah. So that's equal to 2 pi f. So my answer will be 2 times 3.1415 times 8.333. What does that equal, please? It's like 49. Uh, 52 point. Okay. Is this example okay? Anda?
Sorry?
Is this okay?
Yeah.
Yeah? Chow, is this okay?
Mm-hmm.
You're writing this down, yeah? Everybody's sleepy, huh? Did you have any assignment due?
No, well, I was working yesterday with them.
Everybody's so sleepy. Right, continue. So, here's the next one. A car takes 5 seconds to drive around a roundabout. Do you all know what a roundabout is? You know what it is? Explain to Kim, who doesn't know what it is. Explain a roundabout.
It's an intersection that's organized without signals.
True, but what's so special about it?
It goes in a circle.
The charm.
Many things are round.
Yeah, but you go to run it.
And then cars go in one direction. They just keep on going in one direction and they exit and enter.
Yeah. Do you have these in Korea?
No,
You don't have roundabouts?
we don't have it.
Ah. Yeah, some countries don't have it. You've seen them here. Where's the nearest roundabout? There isn't one near the school.
I have seen one here from all the way back from the airport.
Yeah, there's a few at the airport. You have to drive around them.
There's
Yeah.
one in the center, I think.
Huh?
There's one in the center,
Is there?
I think.
Where? I don't think there's one in the city centre. You know what I'm talking about though, don't you? Yeah. So the car takes 5 seconds to go around it once, and the roundabout has a radius of 6 meters. I want to know how fast is the car traveling. That is, I want to know the V. Okay, I want to know the V. What information do I know? So that's 5 seconds. What is that? T. Good. And the 6, what is that? R. Good. And what is it that I want? The V. I will give you 1 minute to figure out the V. Have a look at your formulas and see how to get the V. Got your V? So, let's see. What formula should I use first? V equals, not W. Try again. Omega R, yeah. Now, do we know the R? Yes. Do we know the omega? No. So what formula gives me omega? 2 pi over T R. Okay. So what is the R, did we say? 6, was it?
Yeah.
And what's the T? 5, was it? Okay. So what do we get for V?
1.26.
1.26?
I go 7.54.
Yeah, 1.26 seems too small. What did you get? 7.54 meters per second. 36 over 5. 7.5. 30. Yeah, that seems right. That seems right. What happened then, Dick? Typo?
80.
Yeah. Okay, are we happy with this one? It's okay. So far, not so hard. Or not so bad, I should say. Right, let's look at another example now.
Wait, I did get it, yeah.
You got it? Okay.
Yeah.
Okay. Continue? So, now, a boy swings 1 kilogram around in a vertical circle. So, tell me, is he going like this, or is he going like this? First or second? Is he doing this, or is he doing this? The second one, yeah. So, he must be, I don't have anything that I could swing around. Just right then. So, he must be turning something around like this, not like this. Okay, so he's swinging something around. It's in a big circle, so it's something at the end of the string. It's 2 meters. And the frequency is 2 hertz. How fast is the object moving? Alright, so this is a lot like the last one, isn't it? Let's just do this one together. V equals omega R. Now, do we know the omega? No. But we know the R. So how can I get the omega? It's going to be 2 pi over T. Right, do I know the T? If we look at the story, we don't know the T. Alright, so how do I get the T? What's the formula for T? 1 over F. So we end up with this formula, 2 pi F R. Because we know 2, we know pi, we know F, and we know R. So we can get the V.
25.30.
Say again, George?
25.30.
Got that?
That's the omega.
No, that's V.
That's
Yeah. Okay, continue. Right. Now, we are getting harder. A 10,000 kilogram plane is banking. Does anyone know what this word means when we talk about planes? Banking.
As in parking?
Parking? No. Anyone know this word, banking?
exactly.
No? No, we don't know this word? Okay, so look at me. So here's my plane, it's flying. Okay. When the plane does this, to turn, we call this banking. Okay. We don't say the plane turns. I know it turns, but we don't say the plane turns. We say the plane banks. Now you might say, why? Why can't I just say the plane turns? It's English, so I don't know why. Okay. But we say the plane banks. This is bank. Okay. So it takes 1 minute for the plane to travel in a circle. What is the centripetal force? And what is the banking angle? That's very hard. I'll do this one for you. Before I do it, why might a plane travel in a circle of a 1 kilometer radius? Very big radius. Why might a plane do this? 1 kilometer radius. Any ideas why a plane would do this? Nothing. Nothing.
General.
For what?
As in why it's doing it. No.
No.
Landing.
Well, it's not landing, it's moving in a circle. So, like, why would a plane move in a circle?
Waiting for permission to.
That's it, yeah. It might have to wait before it can land, okay? So, let's draw the picture here. Now, to do this, I need to draw 2 pictures. So the first picture is if I'm looking from the sky, looking down at the plane, okay? So, here's the plane here. That's the front. So it's going around in a big circle like this, okay? And we know that the radius is 1 kilometer. And the mass is 10,000. So that's 10 to the 4, isn't it? 10 to the 4 kilograms. And we also know that the time is 60 seconds. So this is everything we know, isn't it? Yeah. Okay, continue. I need to draw another picture now. Okay, this picture is a little bit harder to draw. So I'll just put it like here. So I want you to picture this is the front of the plane. Okay, and here's the pilot. Okay, that's like the nose, and there's a wing here and a wing here. So we're looking at the front of the plane. Okay, there are 2 forces on the plane. What are the 2 forces on the plane? Gravity is technically 1 force for sure. So that's acting down, and that is 10 to the 4 G. But what is the other force? Yeah, like a thrust from the engine. Okay? Where should I draw that force? We call that force, by the way, the lift force. So where should I draw that?
Upward.
Yeah, you'd think it would be like up like this, but it's actually perpendicular to the plane. That's where you get the lift. Okay? So we call that force L for lift. Yeah? Is that okay? Is that okay? You look unhappy with this.
What is not like
Because what happens is you get the thrust from the wings. So what happens is the air, it would come in and hit the wing and make the thrust force perpendicular to the wing. So it's like, if this is the wing, the air would come in and it create a force up this way. So if you turn at an angle, it still has to be perpendicular to the wing. Yeah. Okay, so what I'll do next is I'll resolve into this component and this component, and I'll call this theta. This is called the banking angle. So how big would this force be? What would it be? How big? L cos theta, and this one would be L sin theta. Okay, now what do we know about L cos theta? Somebody tell me why we know L cos theta equals 10 4 G. Yeah, but why should they be equal? Exactly. If the L cos was bigger, the plane would be rising. If it was smaller, it'd be descending. So they have to be equal. Okay, so we're happy with that. But what about this L sin theta? What is that doing or equal to? What do we think? That's it. This is the centripetal force. Because if you look at this picture up here, there must be some force towards the center. It can't be this, and it can't be this. It can only be this one. That guy matches up in this picture with that guy. Now, we have a formula for F. What is this? No, I'll just write down F first. Okay. Now, I'll just pause for a minute to let you write all this down. So far.
Is a pin always?
Yeah, banked, yeah.
It's not.
No.
Horizontal.
No, it's actually banked as it goes in a circle. By the way, whose country has high-speed trains? They have high-speed trains in Korea? Anyone else that's got China have high-speed trains? So there's only we use banking for planes and for trains. So with the high-speed trains, when they're going very fast and they turn a corner, some trains actually they bank. Yeah. So we can use the word banking to describe trains as well that lean when they turn. Yeah. Okay, continue with this now. Yeah. So let's have a look at this equation first. So L sine theta equals F. But what did Newton say F equals? F is equal to A. Yeah. A. Now, what did we say centripetal acceleration equals? What formula do we have for centripetal acceleration? Do you see it in your formulas? For A? V squared over R. Yeah? So I'll call this equation 1, and equation 2 is L cos theta equals 10 for G. Anybody got any smart ideas on how I could solve equation 1 and 2? Any smart ideas? What could I do? Well, tell me what we know. Do we know L? No. Do we know theta? No. 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 Do we know M? Yes. Where's my green gone? Oh no, go away. We know M. Do we know OR? We do. We know 10-4, obviously, and we know G. Do we know V? No, we don't know V. Right. How do we combine these two equations to give us one of the things we don't know?
V equals omega r.
Good, good, good. So, you're saying first we should replace V with omega or. Yeah. Oh, sorry, that was V squared, wasn't it? Yeah. So that's now omega squared or squared. Good. Do we know omega? No. But we could know omega because we know what the T is. And do we know or? We do. Okay, so now we're making progress. Right, so let me rewrite these again. L sine theta. What does omega equal? Omega equals 2 pi over T. So I can change this into, oh my goodness, M 4 pi squared over T or. What happened to my square here on my or? What happened to this? It cancelled with that. Yeah? And the omega squared is this squared, which is there. Oh, sorry, what's my mistake? That should be T squared. 2 pi squared over T squared. Okay. Right. Trust me, this looks much better. Because we know this, 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 we know this. We don't know this and we don't know this. So now we're ready to go. What to do next? Who's got a brilliant idea on what to do next? Anybody? Shall I show you? It's brilliant. Watch carefully. Next we divide. So L divided by L? No L. Sine divided by cos? Who knows what sine divided by cos is? It's tan, very good. Tan theta equals M, we know, 4 we know, pi squared we know, or we know, T squared we know, over 10-4 G we know. We know everything on the right, so we can now get theta. So we end up getting, put it here, theta equals tan inverse M 4 pi squared or 10-4 GT squared. I told you this one was hard. So let me type that in for you. Okay. Shift tan inverse M. Oh, actually, I can do some cancelling before I type in. What does M equal? What's M? 10 to the 4, isn't it? So can you see that this guy cancels with that guy? Yeah, okay. So this is 4 shift pi squared. What did I say the radius was? A kilometre, wasn't it? And what's the time? 60 seconds? Yeah? So, should this be a big or a small angle? What do you think? Small angle. Oh, no, that's too big. Did I forget anything? 48 degrees? Alright, maybe it's 48 degrees. That's pretty big. The plane is going like this. Yeah, maybe. Maybe. I can believe that. 48 degrees. Seems believable to me. Small problem, we still need to get V. So what would be the easiest way to get V? Let's see. Omega squared or? Would that be the easiest way to get V?
Use just omega or.
Sorry, I didn't mean to say squared. V equals omega or. Omega is 2 pi over T or. So let's calculate this. 2 pi over T. Okay, should this number be big or small? Do planes usually move fast or slow? Okay, so I don't know. We want this to be a good few meters per second. At least 10 meters per second. You know, if Usain Bolt can run at 10 meters per second, then a plane should be more than 10 meters per second. So let's see what we get here. Yeah, okay, that's fine. 104 meters per second then should be big enough. So 105 meters per second. Okay, so that's the answer to part 2. What's the V? This is a hard one. It's a hard one. Okay. Tell me when you're ready. Got that? Continue? Yeah? Okay. No, okay, no problem. Maybe you need coffee, Kim.
I drink coffee.
Ah, maybe that's the problem. You only drink tea? Or no tea?
I drink tea.
You drink tea. Korean tea?
Well, like Japanese.
Oh yeah, okay. So, like flavoured herbal tea. Yes. Ready?
I can't get validity.
Maybe I mistyped it. What did you get?
90.
90 degrees. That means the plane is like this. It's quite a problem.
It's Robert.
Yeah. That's a problem.
Oh, never mind.
It's okay.
I squared it on them.
Okay. Right, continue. Yeah. Yeah, last example. This one, what I like to do first, before I do it, is I like the students just to draw the picture of what's happening. A ball rolls inside a sphere. Do you know what a sphere is? Yeah, Kim, do you know what a sphere is? Chow, do you know a sphere? Kim, explain to Chow what a sphere is. How would you describe a sphere? It's kind of like a circle. What else can we say about it? It's more like a ball, isn't it? A sphere is like a ball.
A ball.
Yeah, it's a sphere. So a ball rolls inside a sphere.
The ball goes inside another ball.
Yes. Now I want you to try and draw this to see if you can get the picture first before I draw it for you. So try and draw this with the numbers. Yeah, now which way does that roll? Draw the arrow. Which way is it moving? Maybe. Any idea on that? George? Got a picture? A ball rolls inside a sphere of radius 5, forms a circle of radius 4.
So the diameter of a small ball is 1.
No. Alright, I'll draw it for you. So, it's quite tricky, but this is what it looks like. So, this is our sphere, and it has a radius of 5 meters. So what's happening is there's a ball inside of it, and it's rolling around inside like this. And this makes a radius of 4 meters. Oh, I told you it was tricky. Yeah. No. Well, how could it be? Because then that would make a radius of 5 meters as well. Oh, this is why you're asking about the 1 meter radius. Yeah, I understand now. Yeah. So look, if you were to look at the ball face on, what you would see is you'd have it here, and it moves along a circle like this. This is you looking directly at the front of it. So what forces act on this ball here? Well, there's the usual weight, which is mg, but what other forces act on it? What's the other force? Come on, don't be shy. What's the other force? If it was just mg, it would fall to the ground, wouldn't it? So what's the other force? Oh, come on, give me words. Reaction force, yeah, reaction force. So that's I don't know how to. I don't know. Oh yeah, this way towards the center of the big sphere. Okay. Right. Now, what we'll do is we'll call this angle here theta. So this one here, this is or cos theta, and this one here is or sine theta. Now we can actually work out the theta. If I draw a triangle here, this side is 5 meters. Are you happy with that? Look, here to here, 5 meters. Okay? How big is it from here to here? What's this side? That would be 4 meters. Because if you go back to the last picture, yeah, 4 meters. So then what is this height here? Yeah. So this angle here, theta, is tan inverse 3 over 4. When you're ready, if somebody could tell me that, that'd be great. Okay. Now I forgot what I'm asking you for. Let me check. I want to know what is the V. That's the V. Right. So let me go back to my picture. what can I say or sine theta equals? What does that equal? mg. And what can I say or cos theta equals? The centripetal force. Because that's what's making it go in the circle. Is that okay? Yeah. Right. Now, what did Newton say F equals? What did Newton say F equals? Ma. And what is A here?
B squared
Over R. Yeah. Yeah. Right. Now, if you look at this formula here, okay, do we know R? No. Do we know sine theta? Yes. Do we know M? No, actually we don't. And do we know G? Yes. Now if I rewrite this, I can say R equals mg over sine theta. Right? And I can put that in there. So I get mg cos theta over sine theta equals mv squared over r. Now this is good because what can I cancel? What can I cancel on the left and the right here? The m's go. Right, do I know g? Yeah. Do I know cos? Yeah. Do I know sine? Yeah. Do I know r? Yeah, I do. So I'll just bring this r up, cross him out, and bring him up here. So now I get b equals square root g or cos theta over sine theta. And I'm finished once I put in my numbers. So that is 9.81. What's the r here? What's the r? What's the radius? Is it 3, 4 or 5? 4, very good. Cos 36.87 over sine 36.87. Okay, whenever you're ready. Maybe I'll type it in actually. $7.23. Got that, George? Yeah? Yeah, no problem. Which part are you at?
Last one.
Okay.
That putting number.
Hard question, huh? Yeah. Now, I forgot at the start of this class that my circular motion lesson, I actually usually do need a double class for it because it's so big, you know. So I don't think we could have done the tutorial today because of how big this was. So would you be alright if we do it tomorrow then? Because I have a feeling that you probably want me to do some of these questions tomorrow after you try them. It's just a feeling. So I think what'd probably be good now is if we use this time here to get started on these. There's how many there? 7 questions. and some of them are quite hard, especially number 7. So can you get a start on this? And if you don't understand, I can draw the picture for you. Okay.